Welcome back, folks, to another exciting JLand Bio exclusive AP Chemistry video. Today we're going to be finishing up Unit 7. 2 more to go, guys. Super excited. Today we're going to be talking about solubility equilibria. So this is actually going to be very similar to the stuff we have talked about previously in terms of writing equilibrium expressions, plugging in numbers, solving using ice tables, but we're just going to be focusing on how much of a material dissolves when you try to put it into a solution. Okay, so that's kind of our big focus for today. Let's see what we got going on. Hopefully by the end of this video you should be able to explain how solutions behave similar to reactions in equilibria, compare KSP, which is the solubility product constant value, and molar solubility. You should also be able to explain factors that alter or adjust the amount of reactant or product in a solubility expression, just like Chatelier's principle, and also be able to explain energy and entropy changes during solution formation. So the previous equilibrium expressions that we've talked about work very similar way to how a solute dissolves in a solvent. This is known as solubility equilibria. Now, some solutes dissolve to near completion, like NaCl, for example. Some dissolve very little, like the ones that are listed as insoluble in the solubility rules on the left, and some dissolve in between. So we have a little bit of a confession to make. When we use general solubility rules and say something's insoluble, it's not truly insoluble, it's just very itty-bitty little slightly soluble. So there is a little bit of a difference here. So if we look on the left-hand side here, we have some solubility rules. So for example, all hydroxides are insoluble except for Na and K. Well, if we look on the right-hand side here, we've got a whole bunch of hydroxides that have a KSP value. Because it has a KSP value, that means that some of it actually does dissolve. But the smaller the KSP value, the smaller the amount actually dissolves in solution. So you can look at some of those exponents and see times 10 to the negative 16th, times 10 to the negative 43rd. Very, very little of the material actually dissolves. Okay. Now, this occurs as an equilibrium expression that we'll take a look at here in just a second. So much like in previous lessons, the solubility product constant exists. So much like in previous lessons, we have a value for K. In this instance, K is the solubility product constant, KSP. Now this behaves just like Kc, Kp, Keq, and you calculate it pretty much the same way. Since a reactant is always solid, KSP is given by the concentrations of the aqueous products of the dissolving of a solute. So before we dissolve a solute into a solvent, it is a solid, and we know that solids and liquids are not involved in equilibrium expressions. So the KSP for the expression of the dissolving of barium sulfate is equal to the concentration of barium ions times the concentration of sulfate ions. Remember that we include exponents on the outside for each, and that is determined by the coefficient of the balanced chemical equation. Okay, so that does play a role as we go through and calculate some of this. So the first question here asks to write the equilibrium expression for the solubility product constant of CaF2. Well, if we look at how it breaks down, so we have CaF2. It's going to break down into Ca plus 2 ions and 2 F minus ions. Okay, so again, stuff that you learned from previous chemistry classes. This is a solid here. Remember, we only include aqueous things. We don't include solids or liquids. We include aqueous things and gases. So for this instance, KSP is equal concentration Ca plus 2 times F minus, and remember that is squared. Okay, that is squared because you have a coefficient of 2, so that goes there. Same process here. We're going to take that. I'm not going to rewrite it. We're going to get 3 silver aqueous ions and 1 PO4 3 minus ion. So again, we do the exact same thing. So our KSP is equal to Ag cubed, and that comes from there, and PO4 with the 3 minus charge. All right, pretty straightforward on how to go through and put those together. Let's move on. So So another new term we're going to talk about is molar solubility, and that is the molarity of each ion that results from the dissolving of the solute in solution. It's also used to describe the initial amount of material that dissolves in solution. Either way you look at it, you're going to have to calculate all of those. All right. So it's calculated the same way if you were to calculate concentration through equilibrium. So you may need to set up an ice table. So if we look at the example below, we have Ag2SO4 as a solid, and we want to look at how much actually dissolves. That's what we want to know, is how much of that initial solid actually dissolves when we go into solution, because that's going to tell us two things: how much initially dissolved, which we just talked about, but as well as how many ions are produced when we put that into solution. So if we take a look here, our initial of our products is 0. Our change, because we're going to lose X on the left side, we gain 2X for silver because of the coefficient of the balanced equation, and 1X for SO4. We then plug those into our equilibrium expression, set that equal to KSP, and then we can easily solve for X, X being our molar solubility. All right? So pretty easy to do that. Let's set up a problem and see what we can do. Solid silver chromate is added to pure water at 25 degrees Celsius. The analysis of the equilibrated, fancy word, solution shows that silver ion concentration is 1.3 times 10 to the negative fourth. Assuming that Ag2CrO4 dissociates completely in water, and there are no other important equilibria involving silver or CrO4 2- ions in the solution, calculate KSP. So this one's a little bit different. We may not have to go through and do an ice table with this, because if I look, I'm actually given the concentration of my silver ions. It's asking us to calculate KSP, so the first thing we should probably do is write out an equilibrium expression. So Ag2CrO4, when it dissociates, okay, what we're going to get is 2 silver ions that are aqueous plus CrO4 2-. Okay, so it is important to know your the different ions that exist. They're polyatomic ions, because it's really helpful to know what breaks into what. So if I write my KSP, that is equal to silver ions squared times my chromate ions. Here's the thing you need to look at here. If my silver ion concentration, which is going to go here, is 1.3 times 10 to the negative fourth, then what number is going to go here? Well, if it's twice as much, right, because we have twice as much ions dissolving, this number here is going to be half of that. We know that from the chemical formula of silver chromate, we know that there must be 2 silver ions in solution for each CrO4 2 ion in solution. So consequently, the concentration of chromate is half the concentration of our silver ions. So again, if our silver concentration, based on the information here, and based on the information up top, is 1.3 times 10 to the negative fourth, then I know that my CrO4 concentration is going to be 1.3 times 10 to the negative fourth divided by 2, because I get twice as many ions of silver as I do chromate. All right, plug that into our calculator, and we get CrO4 concentration 6.5 times 10 to the negative fifth. So now I just simply plug those into my equilibrium expression and solve. So what we get is we get KSP. So we just plug these values into our equilibrium expression. So we're going to have 1.3 times 10 to the negative fourth squared times 6.5 times 10 to the negative fifth. And then we solve. And what we end up with for our KSP is 1.1 times 10 to the negative 12th. So you can see we're dealing with concentrations that are really, really quite small if we think about it, okay? So do keep that in mind as we move forward. It's very easy to calculate KSP from this. Just also keep in mind you need to write your equilibrium expression correctly. And then also make sure that you remember that the concentrations are directly related to the coefficients of the balanced equation. So that does play a role in how we go through and figure this out. All right, let's move on. The KSP for CaF2 is 3.9 times 10 to the negative 11th at 25 degrees Celsius. Assuming equilibrium is reached, calculate the molar solubility of CaF2 and determine the concentrations of Ca plus and F minus. All right, so pretty straightforward here. The first thing we need to do, again, is write an equilibrium expression for KSP. So let's start with that. So our KSP is equal to, and you can kind of, as you get better with this, break this down a little bit easier, because you kind of get an idea of how many of each ion you're going to get when you put it into solution. So CaF2 breaks down into Ca plus 2 ions plus 2 F minus ions. All right, so our equilibrium expression, we're going to have Ca plus 2 F minus, and that's going to be squared. Okay, so if we think about this in terms of an ice table, pretty straightforward. So let's go ahead and make our ice table. We'll just do that over here since we already wrote our equilibrium expression. Okay, we're not too worried about the salt because that is a solid. Okay, we don't really include that here, but whatever dissolves here, we're going to gain X here. But keep in mind, because of this, we're actually going to, so we gain X here, because again, our concentrations initials start off as 0. Remember that we're going to gain 2X here. Okay, so that is pretty important because we have X, and this is going to be 2X for our concentrations at equilibrium, and then we just plug those into our equation. Since we know KSP, and we know that we're solving for X, we can just plug those numbers in and solve. Pretty straightforward on how to go through and solve that. So what we end up with is our KSP, which is 3.9 times 10 to the negative 11th equals X times 2X squared. So when we combine all of those like terms together, what we get is 4x cubed equals 3.9 times 10 to the negative 11th. We're going to take the cube root of this, and we're going to divide by 4. And that'll let us solve for x. And therefore, x equals 2.1 times 10 to the negative 4th. And that is molarity. So that tells you that is your molar solubility of CaF. That is also the concentration of Ca in solution at equilibrium. And then for F, the concentration would just be doubled. So we get 4.2 times 10 to the negative 4th. Okay. So that was how you'd go through and you would calculate all your concentrations. Okay, now in some of the AP questions, especially multiple choice ones, it actually just asks you to get to this point here. It doesn't ask you to do any calculations with it, but it does ask you to go through and set it up. So just be aware of that. The key thing to remember here is this 2x goes in to your F concentration, so you get some really unique numbers here. And then you have to do some interesting calculations in order to be able to go through and solve the rest of your problem. So just keep that in mind. So just a few more things to keep in mind. Using Le Chatelier's principle, we can consider what happens when an ion is added into the solution. So for example, if I look at the example of CaF2 producing calcium ions and fluorine ions, the addition of anything that would produce either Ca plus 2 or F minus ions in solution would push the equilibrium to the left and would decrease the solubility of CaF2. So for example, if I added calcium chloride to the solution, well, that's going to dissociate into calcium and chlorine ions. The chlorine ions aren't going to have an impact, but the calcium ions are going to cause the calcium concentration on the right-hand side to increase. And as we know, when we increase the concentration of something on the right-hand side or the product side, Le Chatelier's principle says that we are going to end up pushing equilibrium to the left. And if equilibrium is pushed to the left, then less is going to dissolve. If we look at the example down here at the bottom, I have lead chromate In solution, I have lots of lead chromate down at the bottom. Some of it's dissolved in solution. If I add something with lead or chromate into it, notice how it precipitates back out. That is because it's becoming a solid again, which is pushing equilibrium back to the left-hand side. Okay? So keep those in mind. When we add common ions into the solution, that can cause an equilibrium shift back to the left, which then decreases the solubility of your reactant. Another example of this is when we're looking at acids and bases. Now, you know that acids typically start with an hydrogen ion and bases with an OH ion. There are exceptions to that, which we'll talk about later on in our acids and bases unit. But changes by using acids and bases can impact the equilibrium as well based on what you are looking at. So let's say we have a base, MgOH2, and it dissociates into magnesium ions and hydroxide ions. If we add an acid such as HCl to the solution above, the hydrogen ions, when they dissociate into solution, will react with the hydroxide to make water. This reduces the hydroxide concentration in solution and shifts the equilibrium to the right. So when hydrogen reacts with the OH, it removes the OH from the right-hand side of the equation. If we lower that amount, then equilibrium is going to shift to the right, just like in Le Chatelier's principle. If we remove a product, then equilibrium is going to shift to the right-hand side. If the anion, for example, of a weak acid and an acid is added, the reaction of H plus and F minus will reduce the amount of F minus ions, shifting the equilibrium to the right. So if the anions from a weak acid, so for example, F minus is our anion in that, and an acid is added, when you add an acid, it dissociates into H plus and whatever the anion is. The H plus then reacts with the F as well, thus creating reducing the amount of F minus in the solution, and if F minus is reduced, then equilibrium shifts to the right as well. Now this will not work if the anion that we're looking at is from a strong acid. So if this were lead chloride, and you added a strong acid to it, or you added an acid to it, remember that strong acids completely dissociate when you put them into solution. Okay, this only works if the anion is from a weak acid. So that's something to kind of keep in mind as we move through these types of problems. So this question asks, which of the following substances are more soluble in acid solutions than basic solutions? So what do I mean when I say more soluble? That means that equilibrium is basically going to shift to the right-hand side when it's in an acid solution. So the first step we need to do is to write the dissociation equations for all of these and see if an acid's going to have an impact. So we have Ni plus 2 plus OH minus. Sorry, 2 OH minuses. So let's say we add HCl to this. If we add HCl, we know it's going to dissociate into H plus and Cl minus. Is the H plus or Cl minus going to impact anything on the right-hand side? And the answer is yes. The H plus is going to react with the OH minus here to form water, which means that the concentration of OH decreases, and if OH decreases, then equilibrium shifts to the right. So this is yes. Okay? And again, that's because the hydrogen from the acid is going to react with the OH in the solution to produce water, which then decreases the OH concentration. Okay? So yes, OH decreases. Okay? How about CaCO3? So again, we add HCl, which breaks down into H plus and Cl minus. Okay. Now you have to ask yourself, is Ca plus 2 or CO3 2 minus from a strong acid? The answer is no. So the CaO3 2 minus ion must be from a weak acid. Okay. And since it's from a weak acid, the same process is going to happen here. That H is then combined with that H2CO3 to create carbonic acid. So as a result, the concentration of carbonate goes down. If the concentration of carbonate goes down, equilibrium shifts to the left. Equilibrium shifts to the right. So as a result, same thing, yes. Because CO3 is going to decrease. BAF2, same process here. We're going to add some strong acid. You have to ask yourself again, is Ba plus or F minus from a strong acid or base. Okay. Answer is no, so this must be from a weak acid here. So the H, again, is going to combine with that F in order to reduce the amount of F in solution. So again, this answer is yes, because the F minus concentration goes down. AgCl. So if we add something like HBr to it, because HCl is a strong acid, remember, completely dissociates. So H and Cl are not going to reform to form HCl. Because when HCl is in solution, it completely breaks down. It completely dissociates. So this is a big fat no. Okay? So again, you just have to look for what's at the end there. If it's you're adding an acid to it and it's a base, or if it is a anion of a weak acid, then equilibrium will shift. If not, then it won't. Okay? Let's move on. Last couple things I want to talk about here, and we haven't really dug into these much yet, but we will in our final unit, is entropy and Gibbs free energy of solution formation. So anytime a solute dissolves in solution, the entropy, the disorder, or randomness increases. So greater material dissolving, greater molar solubility, more entropy. Okay, entropy is just the amount of disorder or randomness in a system. So if I take a solid, I put it into a liquid, the solid and liquid actually have very low disorder. They're very organized, as you can see in the diagram. When I place them into solution, the amount of randomness or disorder increases. So therefore, the entropy increases. Now, entropy is represented by delta S. You may want to write that down. That is pretty important. Entropy represented by delta S. And then Gibbs free energy is essentially the relationship that balances between entropy and enthalpy, which we've talked about a little bit. We'll talk definitely more on this a little bit later. But what you need to keep in mind for now is that if Gibbs free energy is greater than 0, then the solution formation is favorable or spontaneous. If it is less than 0, the solution formation is non-spontaneous and therefore is less likely to form. So if delta G is greater than 0, the solution is more likely to form because it is a spontaneous process. If it is less than 0, then the solution formation is non-spontaneous or very unlikely to actually happen. Okay, so that's kind of the final stuff for this particular unit. Again, we're going to practice with this quite a bit in class, so just kind of keep these basic things in the back of your mind, and hopefully it'll make a lot more sense as we move forward. Have a great day, guys. We will talk to you later, and have a great day. Bye-bye.